says turn it up. Okay, yeah, welcome to North Middlesex High School and our special program, Elements of the Blues. Before we bring our honored guests up to the stage, I'd like to take care of some housekeeping for those that may not be familiar with the building. There are emergency exits in case we have to leave the auditorium on the sides of the stage and of course in the doors that you came in. But if we do need to exit in a hurry, it might be good for some folks to go out that way. There are lobby bathrooms, the ladies' room and the men's room, and for handicapped accessible, if you go down the hall and around the corner, follow the signs, there's handicap bathrooms. The program printed before I got all the names on, so I need to give a special thank you shout out to our wonderful tech gals. We would be literally in the dark without these ladies and other things. So Kayla Norton, Meredith Morrow, and Adrienne Paradis, thank you so much for your help. And the service learners that are out in the lobby selling refreshments, thank you for your support. And there are some books, Dr. Sherry's books for sale in the lobby, and you can see one of the students. A little bit about what the program is going to be. It's going to be loose like a good blues performance, but we're going to start with some music, and then Dr. Sherry is going to enlighten us on his work with the periodic table, and then back to some more music. And our dear friend and Ronnie's manager, Debbie Blanchard, is going to come to interview Eric and Ronnie, talk a little bit about how they started their careers, and mostly to inspire the students and see how a career path could be. And you don't have to just be down one narrow trail, but you might meander a little and maybe make an unusual combination. So it'll be interesting to hear how they found their way to their careers. Okay, so without further ado, there is no intermission, by the way, so if you need to sneak out, feel free to do so. Let's welcome all the way from Los Angeles, California, and West Groton, Massachusetts, Eric Sherry and Ronnie Earl.
So we've never played together, and it's a real privilege and honor for me. He's a true gentleman, and I'm just going to play some blues, and we're going to see what happens. So you know as much as we do. Oh, you're such a kind and beautiful audience. Thank you. I think before we let the doctor speak, I'd like to take a moment to thank Dr. Horvath, my wife, for putting all this together. By all, pretty amazing.
One, two. Okay. Now that we've got the serious business out of the way, here is the intermission. So, first of all, thank you very much for coming. I understand there was some basketball game or other that was on tonight, so I was told that nobody was going to come. So that's pretty good for nobody. Almost a packed house, right? So thank you very much, Donna, for organizing this. This is a dream come true for me. This is the first time I've done one of these. I mean, I've been talking on the periodic table and chemistry pretty much all around the world for many years now. But I'm also a blues guitarist, a hobbyist, and this unique opportunity came up, which I just had to grab. So let me launch into my talk. You've seen this already. This is how it all started. I published an article in Scientific American just about a year ago, which had this title, Cracks in the Periodic Table. It was a bit overdone, by the way. The editors like to be sensational to sell more copies. I wasn't really referring to genuine cracks in the periodic table, but, well, I'll get on to the subject of cracks in the periodic table. I was asked to say a little bit about myself. There's a blurb that appears on the top of these articles. So I rather, what's the word here? Tentatively said that I was a serious blues guitarist, and I've never dared say that in a serious article before. And guess what happens? Donna read this in faraway Massachusetts. Where are we here? Townsend? World's End? World's End? No, sorry. That was me, right? Townsend, Massachusetts. And she said, she got in touch and said, would you like to come? My husband happens to be a famous blues guitarist, Ronnie Earl. I said, yeah, I know Ronnie Earl. I've got 3 of his records. How can I refuse? So here I am. The day has come. We took the night flight yesterday and came in at 6 o'clock in the morning. Luckily, it wasn't snowing and so on. So. Okay, so here's one of my books on the periodic table. Here are several more. And the periodic table. Everybody loves it. Scientists love it, but it's not just scientists. At the recent opening of the Winter Olympic Games, before Putin became a bad person, you may have noticed, those of you who are into the periodic table, that one of the things they featured in that opening ceremony was the periodic table. They went through the Russian alphabet, and for P they went with periodic table, which is of course a Russian invention. At least one of the discoverers of the periodic table was a Russian chemist, Dmitry Mendeleev. French is the official language of the Olympic Games. So that's why it's translated into French there. And then the next moment we saw the elements descending and so on from that marvelous opening ceremony. Now the periodic table, as well as being a scientific icon, has become something of a cultural icon. More and more people have latched onto it. Artists like the shape of the periodic table. Here is that iconic shape which is being used, and it's instantly recognizable to those of us who recognize it. And you have the twin towers there with hydrogen on the left and helium at the top. And see if my laser pointer's working tonight. Yes, hydrogen and helium. And here the artist is using it just as a motif, and then some abstract designs. And here's now you can get the periodic table of almost anything these days. Literally almost anything. Fruits and vegetables, and periodic table of printmaking. Advertisers have latched onto the periodic table. This is, I think it's the Gap. I think if you see right down at the bottom, you might be able to see the symbol for, anyway, I'm not here to advertise Gap, right? Unfortunately, they got it a little bit wrong. Helium is not in the same group as phosphorus, but what can you do? Now, this is my favorite, of course, the periodic table of guitarists. You can recognize some of your favorites here. Frank Zappa is in the first period, towards the right-hand side, and Stanley Jordan in the middle, right at the bottom, and many others. Who else can I recognize? Mike Stern, second row on the left there, played with Miles Davis, among others, and so on. Chuck Berry, right above Stanley Jordan. I could go on, but I'm here to talk about the periodic table. Is anybody else you recognize on there? No? Let's see. T-Bone Walker, where's that? Yeah, use the Rosetta Tharpe. Yeah. No, that's Chuck Berry. Surely that's Chuck. That's T-Bone Walker. Yeah? Okay. Okay, now, when it comes to periodic tables that chemists and physicists have designed, there have been literally over 1,000 tables published. And with the advent of the internet, even more periodic tables have been published in all shapes and sizes. This is a sort of a Christmas tree periodic table. And here is a circular or clock face periodic table. For those of you who don't know, the basic idea of the chemical periodicity is that if you arrange the elements in order, and originally it was done in order of atomic weight of the elements, every now and then as you walk through the elements, every now and then you get a repetition of an element, an approximate repetition, which is very strange, right? And to this day, this hasn't been fully explained yet, although there are some good candidate theories to explain this behavior. And so what better way of doing this than through a clock face, which also shows periodicity. And, you have the number 12 at the top, and you go through 12 hours, and you're back to 12 again. That's the general idea of chemical periodicity. The elements recur approximately, such that there are some elements that are similar to others. Here is a rather nice periodic table in the form of a galaxy. Here is the coat hanger periodic table, or inverted coat hanger. And there are pyramidal periodic tables, and there are, whatever shape that is, hexagonal periodic table. There are literally over 1,000 of them, all claiming to be better than the previous one and highlighting some property that somebody else hasn't. And we all like to have disputes about which is the better one. And there's a sort of cottage industry of periodic table fanatics who worry about these things. Here is a spherical periodic table. Here is a Christmas tree periodic table. This is the one we were talking about at dinner. Here is a wooden periodic table. What would you call this? Well, periodic round table, as the label says. Here's the elephant periodic table. Here is a really nice one that came out of Time Life magazine, I think back in the 1950s, very striking colors. So the basic idea is that here the elements that are similar are shown in these various segments. So for instance, fluorine, chlorine, bromine, and iodine are very similar elements. So this is a very useful tool for chemists. And they can, to this day, predictions can be made on the basis of the periodic table. For instance, when a few years ago, it's now about 20 years ago, it was discovered that there was such a thing as high temperature superconductivity. Superconductivity is the property whereby if you put an electric current into a metal, if you, provided you cool that metal down sufficiently to a sufficiently low temperature, the current can continue almost endlessly. It's a really remarkable property. Usually the current will fade in a matter of minutes or even seconds. But with superconductivity, the current has been maintained for about 2 years is the record. Now this usually happens under very, very low temperature conditions. It was discovered that you could do this at higher temperatures, by which I mean about 30 degrees Kelvin, which is even colder than it is around here, a lot colder. So the search was on for compounds that would do this at even higher temperatures, because the higher the temperature you can get this to work, the more useful it is. You wouldn't have to cool things down to these ridiculously low temperatures if it could be done at higher temperatures. And the way that people went about trying to find new compounds was to quite simply look on the periodic table and to argue that if, let's see where it is on here, it's lanthanum, which is hiding somewhere, and it's going to be up here somewhere. If a particular element worked, just by looking in the periodic table, you can make a good guess about whether another element might work. And sure enough, it was found that the element yttrium worked not just as well, but even better. So that's just one example of the continuing use of the periodic table. It's not just something that hangs on the wall of a chemistry lab or a physics lab. It continues to have vital importance. And that's why it's the central focus of many chemists, physicists, geologists, biochemists, and many other forms of scientists. Here's a ribbon-like periodic table invented back in 1898. This has been around for about 160 years now. If you look on YouTube, just on YouTube, I found some time ago now almost 250,000 hits. That's just on YouTube. And if you look on Google, I found almost 27 million hits, which is remarkable because it's more than relativity theory gets, and it's more than quantum theory, these two very, very important theories of physics that usually get all the limelight. For many years, chemistry was in the shadows of, has been in the shadows of physics and biology. Chemistry kind of sits in between physics and biology. And maybe because it sits in between, it tends to be ignored. If you go to a bookstore and look for, you'll find a ton of books on physics, popular physics, and you'll find another ton of books on biology. And if you're lucky, you'll find 4 or 5 books typically on chemistry. This has begun to change, largely as a result of the popularity in recent years of the periodic table and the elements. Okay, so how am I doing with time? How much time do I have? I'm getting carried away here. Keep going. All right, that's good. One of the interesting things about the periodic table is that it is not yet in its final form. It's not yet settled. And there are some arguments, disputes, controversies, I think is how you was, about precisely where certain elements should lie. And 2 of these controversies concern hydrogen and helium, those 2 elements I pointed out at the beginning, the top of the twin towers in the periodic table. Okay, here's the gist of the idea that I alluded to a moment ago. Periodicity is about arranging the elements in a line using some criterion. Here I'm using atomic number, the number of protons in the nucleus of an atom. And then I've colored them in this way. The periodic table, of course, is a 2-dimensional array. This is not yet a periodic table. This is a 1-dimensional sequence of elements. How does this become a table? Well, you take an imaginary pair of scissors and you snip the red section, the blue section, the green section, and then you paste the blue section underneath the red, the green underneath the blue, the orange underneath that, and you get the beginnings of a periodic table. There's a complication in that you have to separate hydrogen and helium, and if there's time, I'll come back to that. But that's essentially the idea. And what this reveals is chemical periodicity, because the elements lithium, sodium, and potassium are all very similar. They're soft metals, which if you put them in water are very highly reactive, very atypical of metals. Things like iron and copper and nickel don't react with water. They just sink and they do very, very little. And similarly for the next group, and similarly for the next group. So the periodic table captures that repetition. A brief history of the periodic table in 5 or 10 minutes, if I may. Where you start is fairly arbitrary. I'm going to start with the Manchester school teacher, John Dalton, who devised a list of atomic weights for reasons we won't go into here. And this is a famous chart that he published. He used some alchemical symbols for many of the elements, which have now been replaced by 2 letters usually, or 1 letter. And on the basis of these atomic weights, people started to look for relationships among the elements. 2 important relationships emerged fairly quickly. One is called triads, one is called Prout's hypothesis. This is Dobereiner, a German chemist who discovered triads. That is, groups of 3 elements, such as this set of 3 elements, which are very similar. Moreover, the atomic weight of one of them is the average atomic weight of the other 2. In other words, if you add the weight of the first one and the weight of the third one, right, about 7 and about 39 makes 46. Divide that by 2, you get about 23. Right? This is a very suggestive relationship. It cries out for some deeper interpretation, which for many years didn't even exist. Dobereiner discovered other such triads. For instance, chlorine, bromine, and iodine behave in that way. Using more accurate values now, you can see that the average of the top number, chlorine and iodine, comes to 81, and that's close, not exactly the same, as the actual weight of the middle element, which is bromine in this case. And it happens again for that next triad, and the next triad, and the next triad. The second important thing that was noticed, this is before the periodic table had actually been discovered. This is leading up to the periodic table. The second thing is this Scottish physician, William Prout, looked at lists of atomic weights and noticed something fairly obvious. You'll see that most of these are whole number multiples of the weight of hydrogen. Hydrogen is the lightest. It has a weight of 1. Most of the others are a whole number of times that 1. So he made the obvious conclusion. Maybe all the elements are made of hydrogen, are composites of hydrogen. And again, you can see that it doesn't work exactly. There are a few exceptions. Right? There are a few elements that are not whole number multiples. This one, this one, this one. Right? And this one and this one. But it happened enough times that it suggested something more fundamental might be lurking. And in fact, this Prout's hypothesis has made a return, even though initially it was refuted, found to be problematical. These days, we believe that Prout's hypothesis is essentially correct because the elements are multiples of hydrogen in terms of numbers of protons, as all the scientists in the audience will nod their heads at this point and say, very good. Okay, the interesting thing about the periodic table, as happens for many scientific discoveries, is that it was a multiple discovery. Right? This is a surprising aspect of science throughout the ages. We read in the books that one person heroically discovers something and gets all the credit, and they're immortalized and the stories are repeated over and over again. But in fact, what often happens is that 2 or 3 or 4 scientists arrive at the same discovery in a matter of sometimes weeks, sometimes a few years. This is a very good example because the periodic table was discovered by at least 6 people over a short space of time. The very first discovery was by a Frenchman, Alexandre-Émile Bégayer de Champcourtois, who arranged the elements in a line. He wrapped this line around a metal cylinder, and then he noticed that if you look down a column, you begin to see the familiar groupings: lithium, sodium, and potassium, magnesium and calcium. Beryllium should be there, but it's slightly off. But this is the very first periodic table. So the world's first periodic table was in fact 3-dimensional. And on the right, there's the actual periodic table, the model of this form of periodic table. A London chemist, Newlands, also discovered a very respectable periodic table. And here we can make an analogy with music, because Newlands himself made an analogy with music. Newlands announced this as the law of octaves, meaning, as in the case of the musical scale, which repeats after 8 notes, in the case of chemistry and the elements, it also seems to repeat after 8 elements. Now, actually, for Newlands, this was a bit of a mistake to make this analogy, because when he announced this at a conference in London, British chemists, being what they were at the time, or maybe still are sometimes, ridiculed the idea, and somebody got up and said, well, you might as well order the elements according to the first letter of the first letter of each of their names. In other words, this is a crazy idea. Why are you even suggesting that there should be any relationship between music and chemistry? And he wasn't suggesting that. He was just using colorful language. But he was right. There is a relationship. At least there is the analogy that every so often there is a repetition, and the repetition happens after 8 elements. And here's a nice diagram which tries to bring this out. This is Newland's table. A Danish chemist and mineralogist who actually came to the United States at an early age. He was a political refugee. At the age of 21, came to the US, and he discovered a very elegant periodic system, which he displayed in this fashion, like the spokes, on a bicycle wheel, in which we can recognize many of the familiar groupings. And then there's this guy, William Odling. He looks a little bit like a famous Hollywood actor. Anybody see a resemblance, or is it just me that sees? Duvall. I was thinking of someone else, but maybe Robert Duvall as well. I think Robin Williams is what he looks like. Right? That is Robin Williams. In fact, I must try and make a connection sometime, and we can have a Hollywood and chemistry evening to parallel this one. Maybe you'd like to get in on. We'll talk. We'll have your people talk to my people. A German chemist called Lothar Meyer discovered another. Well, what he did, not only did he produce a periodic table, but he produced this very striking graph, which is displaying atomic volume against atomic weight. And you can see periodicity kind of jumps out at you. If you didn't believe in chemical periodicity before, after seeing this diagram, you would have to believe it, because you can see that the group 1 elements show the peaks in this property. Right? There's repetition after a certain interval. Now, most of the credit, of course, goes to the Russian chemist I mentioned earlier, Dmitry Mendeleev. Not only he's the 6th and last of the major discoverers, and yet he gets most of the credit. But that's deserved, because not only did he discover the periodic table, but he left spaces for elements that had not yet been discovered, and he went further. He predicted their atomic weights. So you'll see occasionally something like this, where there's a dash, and he predicts an atomic weight of 44, he predicts an atomic weight of 68, and many of these elements were discovered, and they turned out to have very similar properties to what he had predicted. This is a famous list of some of those properties. So here's Mendeleev predicting an element that he called eka silicon, meaning one like silicon. in 1871. Here's his set of predictions for various properties. And when it was discovered and named germanium 15 years later, you can see that remarkably accurate. So it almost looks like magic that Mendeleev could have known in advance, right? 15 years in advance of this thing having been extracted, discovered. He knew what the properties were going to be, with one little minor exception here, which is not all that important anyway. But again, the textbooks get a little carried away about how wonderful Mendeleev was. And if you look more closely at all the predictions he made 18 predictions. Half of them turned out to be incorrect. That's not a very good success rate. 50% is almost of astrological standards. Right? Astrologers typically get things right 50% of the time. But this is not supposed to be astrology, it's supposed to be science. At the turn of the 20th century, physics began to invade the periodic table, meaning they made discoveries whereby they began to think that they could literally take over the periodic table, explain everything about the periodic table. J.J. Thomson discovered the electron, and the electron turned out to be the key explanation to why the periodic table is what it is. Marie Curie and several others discovered radioactivity that showed that the atom was not unsplittable, as was originally thought. That's why it's called atom, meaning uncuttable. Well, it is cuttable, and you get various things out of it, such as the electron, and fundamental particles emerge from the atom. This cast new light on the nature of the periodic table. Rutherford discovered the structure of the atom, namely that it had a central dense nucleus. And this man is, does anyone know his name? You can't answer this one. It's too easy for you. Huh? Moseley, yeah. Moseley discovered atomic number. Moseley discovered that actually the real ordering principle for the periodic table shouldn't be atomic weight, but it should be atomic number, the number of protons. And if you use this new criterion, certain problems get sorted out. For instance, there's something called pair reversals. Anyway, this is boring stuff. So, Niels Bohr imported quantum theory into the structure of the atom, and the electrons were assigned to various electron shells. And Wolfgang Pauli discovered the fourth quantum number, and then anyone who's studied high school chemistry or beyond has been subjected to this kind of thing where quantum numbers are assigned to electrons. And again, I'm just going to... Okay, there are really three forms. There aren't thousands of forms of but there are really three, when it boils right down. There are short form tables, just like the original Mendeleev forms, which are 8 column tables. Here's the idea of octets, right? The law of octet. There's a repetition after 8 elements. Then there are the medium long form tables, which is the most familiar one. There is the hydrogen and helium of the twin towers, as I keep calling them. And then you'll notice that in this form, this thing at the bottom seems to be disconnected. In fact, it's not disconnected, and it's only shown like this because if you included that in its correct place, the periodic table would be too wide, and it would stretch all the way to about there. So what's usually done is to relegate those elements, which include the rare earth elements, as they're called, which these days are very important for geopolitical reasons. And there's another lecture there, which I will not give right now. You get this table. So this is the long form periodic table, which is in a sense the most correct, because instead of having these elements as a sort of footnote, these are placed in their correct place, which turns out to be there. You have to open up the periodic table between groups 2 and 3 and insert all that in there. And you get this. Hydrogen is a mysterious element in that it doesn't seem to know where in the periodic table it should sit. It's traditionally placed in group 1, part 1 of the twin towers, but it's also been placed here in group 17 because it forms an H- ion. It accepts one electron, just like these elements accept one. It's sometimes allowed to float majestically above the periodic table, because of not being able to decide where it should go, right? And for other weird reasons, some people have even placed it there in the periodic. Where should hydrogen be placed? Then there are issues about where helium should be placed. And then there are issues about where lanthanum, actinium, lutetium, and lawrencium should be placed. Well, here's one suggestion that I've made to try and resolve this. If you use triads, instead of using atomic weights, you can use atomic numbers. And now triads become absolutely exact. Because if you look at the chlorine, bromine, iodine triad, bromine has got exactly the average atomic number of these two. Right? 17 plus 53 divided by 2 is exactly 35. Similarly for all the other triads that work. So if we try and maximize such triads, we might be tempted to move hydrogen to there. At the moment, hydrogen is not sitting in a triad. Right? 1 plus 11 is 12. 12 divided by 2 is not 3. But if you move it to there, it now becomes part of a triad. So my suggestion has been that it should be moved there. This is a periodic table in which not only has that been done, but the periodic table has been sliced there, and we begin, because we like to start with 1 in the top left-hand corner, we can keep on doing that if we now do this. What about helium? Helium is debatable because it seems to be like a noble gas because it's completely unreactive. On the other hand, helium has 2 outer electrons, which suggests it should go in the same group as elements with 2 electrons. So it's, am I taking up too much time? No? So here's one way to do this. You can actually move helium to be in the group with elements that have 2 outer electrons. And then something rather interesting is sometimes done. That is, we slice the periodic table here, and we take this entire block and put that entire block to the right-hand side, and we get this very elegant left step periodic table, which, by the way, has the additional advantage that now all the periods repeat. 2, 2, 8, 8, 18, 18, 32, 32. In the conventional table, the first period does not repeat, which has always left people wondering whether that was correct or not. So in this table, everything repeats. Nature is completely regular. But the price to be paid is that chemists don't really like the idea that helium should be grouped with these metals. Helium is completely unreactive. And so there's a sense in which helium really does belong in this, a chemical sense. So this highlights the tension between chemistry and physics in these matters. Then there are debates about group 3 elements. Some periodic tables you'll see scandium, yttrium, lanthanum, and actinium. Other periodic tables you'll see scandium, yttrium, lutetium, and lawrencium. Is there a fact of the matter? Is one more correct than the other? I believe that it is, because again, you can make a perfect triad out of these elements, but not these elements. Right? If you try and make a triad out of this, it's way off. It should be 57, but it comes out to be 64. Whereas with this, it is perfectly correct. Okay, let's see. And that's it. I thank you for your patience. And we can now go back to some music. We have time for 1 or 2 questions? Anybody have a question they'd like to ask? Yes.
Earlier, you were mentioning about the way that the theory.
Yeah.
Could you elaborate on some of the most major theories?
Yes. The simple explanation for the periodic table is in terms of electrons. And as you probably know, it is that elements that belong in the same group do so because they have the same number of outer shell electrons. It comes out of quantum theory. So when Niels Bohr started applying quantum theory to electronic structure, it became clear that that was the reason why certain elements fall within certain groups. And that's why it's interesting to look at cases like helium, because according to physics, helium should be in group 2, According to chemistry, it should be in group 18. Right? Now, does physics explain chemistry? Yes and no. Fundamentally, physics is the most basic of all the sciences, and chemistry is sort of more superficial, right? Just in the same way that biology is yet more superficial to chemistry. So biology depends on chemistry, sociology depends on biology, and so on. This is the question of reduction. Sorry, I've gone off on a complete tangent there, but yes. Okay, let me take the second question first. When Moseley discovered atomic number, it became clear, unless something really weird is going on, that there are no missing elements. In fact, this book, if I may just digress onto it, this book is about why is it a tale of 7 elements? Because when Moseley discovered what he did exactly 100 years ago, in 1914, it was realized that the periodic table is ordered according to atomic number, meaning number of protons. And it was realized there were just 7 elements missing. There's nothing in between. Whereas when it was done according to atomic weight is a sort of an irregular property. Sometimes there was an atomic weight gap of 2 or 3 or 4 between 2 elements. So there was always some doubt as to whether there was a missing element or not. We know there are no missing elements. Of course, elements have been produced, artificially synthesized beyond the natural 92. Okay? But within the 92, there's nothing missing. Unless something really strange is going on. It's conceivable, right? Because protons are made of quarks, and there are 3 quarks to a proton, that there might be elements, 3 elements to each element. Okay? That's rather speculative. But that's one very weird possibility that has been played with by physicists. And what was your first question?
Why did you standardize, or did you have standardized?
For convenience, as I said, that we've abandoned the Mendeleev table because the Mendeleev was the short form table. I have to go back several. The Mendeleev table was that one, right? Okay, the reason for that is that Mendeleev put the transition metals in with the main group elements. So he would have put titanium in with carbon because titanium forms +4 ions. Similarly, vanadium forms +5 ions and so on. But really, there's a stronger similarity between titanium and elements below it than there is between carbon, silicon, and tin and lead. So you get a better account of chemical periodicity by making that separation. Then you make that separation yet again, and you get the long form table. But the Mendeleev table is not wrong. It's just not displaying periodicity as well as you can display it. Good. No more questions. Yes, he wants to ask another question. My favorite element. My favorite element is number 72, hafnium, which is named after Copenhagen. And the only reason why that's my favorite element is because I got to meet Sir Karl Popper, the famous philosopher of science, as a result of that element. He had written a paper in which he said quantum mechanics predicted the properties of hafnium. And I knew that this was wrong because I happened to work with an advisor on my PhD who gave me certain papers that showed me that in fact it was his father, my advisor's father, who had suggested to a couple of scientists where to look for hafnium. So Popper was wrong. I wrote Popper a letter and said, as politely as I could, "You're wrong." Right? And I put my phone number on the... This was some 20 years ago when people still used telephone. And he called me and he left a message on answering machine. I was living in London. He was living in London. He'd gone into hiding. And he was in his 90s. He said, I want you to come and discuss this with me. And I had the most amazing experience of sitting with Karl Popov, and he kept me there for 3 hours and told me about when he was having a conversation with Einstein, when he met Wittgenstein, and so that's why Hafnium is because as a result of Hafnium I met Karl Popov.